Okay, now things are going to get a little tricky. What if we want to delete, let's go back over here, the 50 or the 35? Well, let me go set up that test case. Whew. Well, if we delete the 50, we want to make sure the 77 is available. That's on this side. We want to make sure the 32 and the 40 is available. All right. Whew. Window Manager seems to be having some problems. And fail. 165. Great. Yep. Oh, we don't even return true on removing the 50. Oh, that's amusing. Huh. Do we not find it? Left. How can we not find the 50?
It never got to the. We're only deleting it if one of the left or right is null. I guess for 50, both.
Well, hold on. What I'm trying to say is here, if left. So it should be here because if the current node is 60, the left is 50, right? And so if the current node's left and the left is 50, we're going to delete left and then we're going to return true. So even though we don't actually delete it, we're still returning true. Unless I'm misreading this statement. It says line 165. Let me run it again because I've seen weird things before. Line 165. All right. 165. It says right here, BT removed 50. It doesn't find it? Interesting. Well, let's go some print statements. Well, those are going to get people. Is it running really slow on your machines too? Or it's like breaking up? Not really? Okay. All right. See, now it's running fine. So we do parent, val, left, and then left is okay. We'll do left, val. Otherwise, we'll do -1. And now it should. Oh, not like me. Not declared in the scope. Yeah. Note. All right, so fail here. So it's at, oh, it starts at, the parent is 50. Interesting. Huh. Do we set this up differently? Oh. Haha.
I think that might be a problem.
All right, we do find a different error, but that's okay. Now it's line 166. Great. Okay. So now we're in the final test case where we can just have an else. So we're at the 50. Said do it the hardest way. So what did does anyone remember what I did?
You took the 48.
Why did I take 48?
Because it's the biggest on both sides.
It's the biggest on the lower side.
Oh, yeah.
Right. Okay. There are hard ways to do this and easy ways to do this. let's go with the easy way. Int find largest. Here's a node. I want to find the largest node. We're going to assume that node is legal. So bt node rover equals node rover. Actually, how do I do it? Rover dash right. Rover equals rover dash right. Okay, we're just gonna keep doing that, and then we're gonna return. I don't even know why I did it that way. Let's do this. BT node. I'm gonna give you a hint. So int temp equals find largest. All right, so what's going on here? What would we find the largest of? Well, if we're trying to delete the 50 and we're at the 60 is a parent, 50 is to delete, then we want to find the largest of 2 deletes left. Okay. Did that a little differently. So let's start this again. So first I want to get the value of the largest element on the left-hand side of what I want to delete. All right, well, I'm trying to delete 2 delete because that's where we are, wherever that is. We want to find the largest of it. So hopefully this will come back with the 48. You know what? Let's find out. Hey, it came back with 48. And it said it passed. Oh no, it failed. Perfect. Okay, so it came back, it found that 48. There are hard ways to do this and easy ways to do it. Don't think of the most efficient way, just think of the way that's most accurate. What do we want to do now?
Switch the value of the 50 to the 10.
Yes, but before we do that, we need to do something else. Because if we were...
Delete the 48.
Yeah, so let's delete the 48. And this is where it gets a little tricky because you don't have access to it because I made these functions not member functions. So, one moment, and I'll show you how to do this quickly. So we have remove rec. We're going to make these private. It is a good idea to make functions private when you can because that tells other people don't call these functions, I'm only calling them. That way you can guarantee certain things with the functions and not have to do extra checks all the time. Hold on. There we go, binary tree. All right, why am I doing that? Because now you have access to this, the actual executing object. All right, do it. Remove, yeah. I think I called it remove. Oh, sorry, go ahead. What were you trying to do? I misunderstood what you were typing. Okay, we have temp, right? And we're trying to remove 50. We have found temp, or largest of the smallest, if I really wanted to type that all out, is 48. So temp is currently this value. What do we need to do to 48? What's that? Oh, perfect. Let's remove temp. Great. We have access to that function now because I made the member function. All right, then what do we do? All right, are we done?
We also need to tell what the root node is.
Are we done with this number 4? I don't know if you understand what you mean by root node.
So, like, for remove the function. Is
Oh, so a good question, and I went on autopilot and forgot to explain why I was doing it. But the reason why I made these member functions is by calling remove, you now implicitly have re-accessed the root node because you're calling it as part of the class, right? So when you call remove, what you're actually doing is you're calling this function here. And since this function has access to the root, it's going to recursively call remove recursive here and start the descent again. Is this the most efficient way to do this? No. But doesn't that make the coding a lot easier? I mean, when you use a library, of course it's going to do this a way more efficient way. And you can probably guess what it's going to do. It's going to actually go where you are and search for it, delete it there, as opposed to searching twice, which is what we're doing. But as I was trying to point out, don't make life harder, because number 4 looked really difficult. I think here, find to delete left. Yeah, so to delete left, find largest, and then remove. I think we're done. Let's find out. Yeah. Not too bad, or at least not as bad as it seemed, right? It's the big trick with the 4th one is basically using your resources. A lot of times it's easier to just, okay, how can I just make this thing work and be accurate and I'll worry about performance later. It's actually a very good way to go about it, worry about performance later, because a lot of the times the code you write doesn't have to be perfect or high performant, it just needs to work in the time that it is, and then at some point you'll find what needs to have the performance improved. A lot of times they care more about it being showing, you can show it, and as long as you can show it working, you can then tell your customer, okay, I'll speed it up, give me a couple more weeks, I'll get it working. Because the other reason why that's important, is a lot of times you show it and they're like, oh yeah, I don't want this at all. Well, it's a good thing you didn't waste all that time improving the code. So, very important, make it accurate first. All right, now, there is a way to combine these two functions. I'm trying to think how.
Only 9 o'clock. Are we going to do it?
It's 9 o'clock. Right. Because I do need to show you one other thing before I go forward. Anyone take a guess on how it's done?
Could pass the volt without work.
Oh, true. All right.
Don't do it, but
Yes, that's true. Not what I was going for. But okay, so to delete, notice here we have 2 deletes left and 2 delete right here is right. Well, what we actually we can go in and pass in toDelete, and then that'll get rid of this part because we can know if it's right or left. But the other trick we have is, notice on this one, we're setting a, hold on, we are setting the pointer to the left. So what you actually need to set is the pointer. And ooh, what's a good name for this? Child. All right. You're about ready to see why I don't show students this. So we don't have to do that up there. What we do here, we still copy this down because we're still working with toDelete. But here we just have star child equals null. I think that's going to be it. I'm not going to run this real quick, but that's it. Yeah, that's it.
Nice.
So, hey, look, it's a double pointer because we're keeping a pointer to the pointer that needs to be changed. So, how do we call this? Well, I guess we'll go ahead and test it, see if it does work. Now I'm going to have to declare it. Let's see, delete generic. So we're going to pass in node. Hold on. Left. We need to generate a pointer to that so it knows that it can change it. And then we're going to pass in node dash left. Because it needs to have a handle to the actual pointer and then where it resides. And then node, is it node dash left, or am I seeing that wrong? Hold on. Yeah, I got it right. Whew. All right, let's see if I typed that correctly. Nope. Oh, never mind. That's an easy one to fix. Node was not declared in the scope. Oh, maybe I can't do it right now. 91. Oh, yeah. Oh, okay, yeah. So part 4 doesn't work in this generic version because you do need to have, right. So you actually have to have not just the child pointer, but you need to have the value as well. Oh, so part 4 is not going to work here. So in this case, oh, what would you do here? Oh, you would have to mess up the pointers. We're not doing that. Because for this part to work right here, we would have to not only remove, we wouldn't remove temp, we would actually grab that node, put it up there, remove that node, and then fix that node down there. I'm not going to do that.
That's the first step to doing it the generic way.
And now you know why I didn't do it the generic way. Let's go back to passing the test cases. Yeah. All right, any questions? Comments? Screams? All right. Oh wait, let's go through the slides. Hey, look, we deleted the 45. It's gone there. Delete the 30. Where was the 30? Oh yeah, 30 is right here. So just took the whole 45 down, shoved it up to the 50. We're good. And then deleting the 80. The 80 was over here, so they deleted and just moved the 75 up. And then deleting the 50. The 50 was right here, just like we did. And they copied, oh, they copied the 48 up there and moved the 45 up. All right. Oh yeah, the analysis. So again, worst case situation, the binary tree could degenerate into a linked list one way or the other. Hopefully that doesn't happen. In which case everything's O of n. But in general, searching and adding as 11 base n yeah, for those two, as well as removing, actually. How many of y'all are discrete? I know I've asked this. Couple? Oh, wow. All taking discrete, right? Oh, yeah, because it's required for architecture.
Yep.
Yep. Ooh, I wonder if I can make it a co-rec. Have y'all taken discrete already? Oh, okay. Ooh. Oh, I can make it a co-rec for this class. Ooh, which proofs have y'all done?
Ah, you're right, we just finished sets, so.
You've done,
Just got to
Yeah, we were into the functions.
Sigma and to note.
have y'all done proof or inductive proofs?
I
That's-
think so.
We're on that, that's our.
Where you have your base case and then you prove for the base case and then you prove,
That's
given
right.
n, you do n plus 1?
I said that's our homework this week.
Okay, so you're to that point, all right. But you done proof by contradiction and proof by, all right. Yeah, all right. We're getting there. Okay. That'd be nice, because then I wouldn't have to say trust me. Trust me. Oh yeah, you could do the non-recursive one. Ugh. We're moving past that. All right, binary tree traversal and functions as parameters. All right, this is very important. And they don't tell you. Oh, here they go. Hey, what is this? Well, it's a function. And what are we sending to the function?
Function point.
Yes, the function pointer. So we're sending a function pointer to the function. All right. Why would we do this? Well, it doesn't tell you. Okay. This is done all the time. The compiler does this a lot for you. Actually, when you're doing inheritance, this is how inheritance is actually implemented. But we're going to manually do the visit function. What's the point of this? Well, actually, let me pause for a moment so we're in a different section.